Good afternoon, everyone. Thank you very much for being here for this online technology meeting on photonics for smart farming. I'm Jeremy Picot-Clemente. I'm a technology expert at EPIC on this topic especially. And before to start, I would like to give you a few words about EPIC. So EPIC is the largest industrial network in the world in the field of photonics. We have today more than 800 members covering all the value chain of the photonics industry, from the component manufacturer to the design company and prototyping company as well, also to the end user and system integrator. We also cover all the photonics application, which is quite wide, from space and defense to biomedical and quantum, and also, of course, including farming and food industry. Our aim is to create a sustainable European photonics industry. And how we do this. So EPIC offers a large panel of services to members. So we offer technology support, market and technology report access on the intranet, networking events and opportunities, access to market, US market, also Asian market, mentorship, HR support with the website Jobs in Photonics, and also investment support. We are also a team of 12 people, all passionate by photonics. I'm personally part of the technology team with my colleague Antonio Castello and Ivan Nikitsky, but we have also a marketing team, logistic team. Few words about the next event we'll organize this year. So before August, we'll have some online meeting, and beginning of September, we'll have some physical meeting with delegation to Taiwan. We'll have also a technology meeting on industrial laser processes, our Optoprim in Italy. We'll also organize a delegation to India. We'll be present at the W3 fair at ECOC as well, and we'll have also an EPIC technology meeting on photonics for quantum and at NKT Photonics in Denmark. Then about online meetings, tomorrow we'll have a new product release. Then we'll also have an online meeting discussing the impact of US tariff on the European photonics industry. And then we'll have also OTM on quantum sensors, so various topics. Mid-IR development for spectroscopy, sensing and monitoring, which could be interesting for you. We'll have something in October on the metrology system and also on materials for photonics chips. So as you can see, we cover all the photonics application. So you can find, of course, one topic of interest for you. And we invite you to check our website. Here is the agenda of the today's event. So 2 hours dedicated to smart farming. We'll start with a presentation by Derek Gunther from Ocean Optics, then Teres Quister from KWS Group. We'll continue with Gaetano Panaggia from Amamatsu, Marc Larive from Exosense, Ariane Tip from IMEC, and René Hein from Qbert Hyperspectral. And we'll end this session with Hugo Texera from Collab Vine and Wines, and you will present the Retina European project. So thank you very much for participating to this event. You can contact us afterward if you need to be introduced to some of the speakers or some of the participants. You will also have time to ask any question you will have. We keep sometimes, 2-3 minutes after each presentation if you have some questions. So feel free to raise your hands through Zoom. And now let's start with our first speaker, Derek Gunther. Derek, you will talk about wavelengths of water using NIR to keep crops alive. And you are talking for Ocean Optics. So thank you very much and welcome, Derek. And please, the floor is yours.
Oh, sure thing. Oh, thanks so much. Thanks for having me here. I'm going to go ahead and share my screen here, and then we'll get into presentation mode. So hopefully folks can see that okay?
Yeah, perfect.
Great. So yeah, as Jeremy alluded, my name is Derek Gunther. I'm Senior Product Scientist with Ocean Optics. We're headquartered in Orlando, Florida, Disney World, where everyone wants to come. I actually live in the Tampa Bay area, right down the road here. And I'm just going to talk to you briefly about using near infrared to keep crops alive. Because what's in the news today? Two big things that are in the news that are related but not immediately recognized as so are the global droughts. We're all hearing about all the drought situations and obviously the heat waves that you guys are having in Europe right now, and avocado toast, very popular, at least over here stateside. Things that with avocado are very, very popular. We have a chain called Panera Bread here. They just released a few salads with a bunch of avocados. So right now in the Western US, 40% of the Western US this summer is in a moderate to extreme drought. So there's a lot of wildfires going on. So, water management is something that people are looking at. And along with that is that the water intensive crops, like I mentioned, are getting very popular. So things like almonds, and we don't always think about this, that every almond, every little one that you eat took over a gallon of water to make that nut. And a single avocado takes 60 gallons of water. Think about how much water is in a 5-gallon bucket. And you need, 12 of those to be able to get an avocado. And cashews are up there too. Those are very popular. So you can kind of see here what the water demand is for some of these crops. And they get very notable in terms of when you scale that up over a large area. That's all to say that there's now a need for deeper insight into how water retention is working over that broader area when you're dealing with droughts and you're dealing with agriculture that needs more water than ever, but there's less water than ever. So how do you deal with that? So before we talk about the NIR stuff, I just want to do a quick overview on our spectroscopy. So our bread and butter are the broadband spectrometers. This is the EPIC group. So you all know this, but just in case maybe you're in another area of photonics, you don't know this, but our core spectrometers are basically a rainbow in a box. We send light in, it bounces off some mirrors, hits a diffraction grating, it splits it into all the rainbow of colors, all the wavelengths, that hits a detector array, and then the software converts that to just a signal so we can see how much energy we're getting at the different wavelength levels, right? So the benefits of this is that it's instant. You get it right away. It's literally the speed of light. Minimal sample prep. It's non-destructive, so you're not eating up sample when you're doing this. It's cost effective for the most part. You can do this stuff in little, sub $1,000 systems, and it's very versatile. So you can tune that rainbow to be in different areas of the spectrum. So obviously we see in the visible range. That's why it's called the visible range, the vis range here. But if you go past the violet, then you're in ultraviolet, right? So you can tune things to look at the UV, the ultraviolet. Then eventually you get into X-rays, you see through stuff, gamma rays, those turn you into the Hulk, the cosmic rays that are the background of the universe. And then you go the other way from the red, obviously you're in the infrared. And then you get into microwaves, cook your food, radar, AM, FM radio, broadband, all that stuff. So what we're going to look at here is the NIR bands, the near infrared bands that exist right around here for water detection. So what does that look like? There's in particular two big active bands at 1450 and 1950 nanometers. And you can get pretty affordable spectrometers that get up to 1700 nanometers because that's where the standard silicon and detectors will go, but then you can go out further for more expensive detectors. This was a set of data from a colleague of mine, Dr. Yvette Matley, and you probably have heard of her because she's really the face of ocean. She's been with ocean for a quarter century, literally. So she ran this study looking at different types of soils at different moisture levels. So you have dry sand at 4% moisture, topsoil that's kind of drier than most, and then premium soil that's a little submerged and that's higher moisture content, and then compost that of course is going to have a high level. And you can see these bands right at the 1450 and 1950 stacking up very coherently. So you're getting those signatures. And this gives you a clear differentiation of both the moisture level and the soil type. We're going to see that in some other wavelength ranges in the next plot on the other page there. But that's the whole idea, is that you can differentiate those moisture levels using these NIR bands very instantly and very accurately. And they're big. This isn't like we're using some sort of deconvolution to see this. This is just raw data right to the detector. You can see those stacks. So this is the type of setup you would be using to run that. where you have your light source, of course, obviously the spectrometer to make the reading, but then you're sending it through some fiber optic and trying to illuminate and then interrogate back up that light signal there. And then we use a reflection standard, in this case, a white standard there. But this is a typical desktop setup that you would use for this. But that's to say, we're trying to talk about this in terms of agricultural, right? So this is about deploying this for watching water retention, because when you have these different types of soils, when in an agricultural setting, you really have to be able to, over an area, you think about how big farms are, you have to be able to pull that data out in a realistic form factor. So what does that look like? You can do that with a handheld device where you're doing more spot checking. Maybe it's a smaller area like a research farm where you're not really trying to cover huge areas, and you can do more of a handheld system that's pretty easy to do. The towers are actually popular. This is a real tower in an agricultural setting that uses our equipment in there. And you can see on the, you can see here all the different these are fiber ports pointing at different angles out. So there's like down, and then you can see like, 5 o'clock, 4 o'clock, 3 o'clock, all going through here. And you can also see, you see this black thing up top here? That's one that's pointing up to the sun, because in the prior one, we were using a light source here, right? So we're forcing the light ourselves. In an agricultural setting, you're almost always going to be using the sun as your light source. So to track that and understand what the sun is doing, and as your source, you can have one pointed up like this black antenna that has a fiber. It's looking at the solar illumination, and then down at the crops, and then you're getting that feedback up into the fiber and the spectrometer. So that's great for continuous monitoring and for fixed locations. Obviously, you're not moving the tower around. But if you want to move around, then you have the drones. And they do make these. I mean, we make an near infrared spectrometer, a small one like this, that can go on, and many other folks do. I don't want it to sound like a commercial, but like, because you can get this from all sorts of suppliers that go on drones, and now you get this top-down view of everything, and you can move that around very efficiently over larger areas. So that's good for like mid-sized farms and whatnot. And then satellite is the next way up, right? You can see how we're stacking this up. We go from handheld to a fixed tower to a drone up into a satellite there. And then when you're using the satellite and you're looking at other bands, that's where you're able to see the different types of environments that you're looking at. So whether you're looking at just surface water or a forest or grassland, desert, plains, all these different things, that's where you're going to get those signatures that are going to tell you what type of ground you're looking at, or water for that matter. And then if you're looking at ground, what that moisture content is using those NIR bands that we talked about. So this was just a quick snapshot. Hopefully I didn't, yeah, so 8 minutes, 8.5 minutes. Quick snapshot of how you can look at water in different form factors in an agricultural setting using these near infrared spectrometers. So thank you so much. If there's any questions.
Thank you very much, Derek, for your nice overview. Any question for Derek? You can raise your hand through Zoom. Huh? Maybe one question from my side, Derek. So you mentioned different kind of I would say integration. So you have this kind of towers, this kind of drones also. So how your customer choose? It depends on the size of the farm, because I guess that a tower is much more expensive than integrating this kind of product on a drone. So what are the main difference? What are the pros and the cons?
Right. So really it would be, if I can well, I won't bother sharing, but if you remember on the hardware picture, I was showing the different sizes. There was one spectrometer that was particularly large. You wouldn't want to put that on a drones, but it gives you higher resolution, higher sensitivity. And so those bigger systems that offer the higher specs that you're maybe looking for, those would be geared for a tower, because then you can, route everything to a bigger fixed hardware setup, versus the drone, you're kind of limited, at least for now, to the size, especially for smaller farms. So then you would use one of our, or anyone else, a smaller unit that would be more drone deployable. So I would say that it could be based on the size of the farm, but it could also be based on the budget and spec needs, the performance needs of the spectroscopy they're looking for, and based on that, what size unit they end up with and whether they can get it up on a drone for a significant amount of time or if it should just sit on the tower based on how big it is. Yeah.
Okay. Yeah, we have a question from Christine. No, please, Christine. You are muted, huh? Whenever you are speaking. Christine? Christine, if we can't hear you. Oh,
Yes, now.
good.
Can you hear me? Okay,
Yes.
sorry. So thank you for the presentation. I have two questions. Is what you were showing, are these pilot installations or are these systems used commercially from the shelf? Question one. And another question is, I'm just curious, what light source are you using?
Oh, right. So, yeah, I can tell you that everything that's deployed right now in the tower or the drones are full. They're not pilot products or systems. They're fully commercialized systems. So, I mean, they all have support for different software interfaces and industrial communications and things like that. So, yeah, they're ready to be deployed in that regard. And then in terms of the light source, for those, especially for the NIR, we're using a tungsten halogen source, something that we call our HL2000, but it's really just a tungsten halogen bulb. So it covers around 350, 370 nanometers up to way up into the 2500 nanometers, 2.5 micron and beyond. So if you were looking at the UV stuff, because then there's a lot more biological things going on there, then you would need to be looking at xenon or deuterium or whatnot. But honestly, like I was mentioning, the sun is such a convenient light source. So as long as you can have a channel tracking the sun and looking what that's behaving like, then you can see as a function of that what's happening based on the reflection of your solar signal. So we're very fortunate to have the sun, at least we're in Florida. So, and you guys, I think all in France and stuff where Jeremy is, I mean, you guys are, that's why you have your wineries and orchards and stuff like that. So
okay, yeah, makes sense. Thank you.
yes, thank you.
Thank you, Christine, for the question. Yes, Henrik from SPIO System. Please, Henrik.
Hello. Derek, thank you for the presentation. What difference the tower-based system to the drone-based system? You said there was a different spec. So is it the wavelength range, or is it, what is the differential between the two systems?
So yeah, there you brought up one of them, which is important, which is the wavelength range. So the more expensive and broader detector that can get up to, let's say, the 2.5 micron, that's in the bigger form factor. That's in the big box. And so that would be something that you would want on the tower. Right now, the small drone base, so the little one, it's about this big. It's like size of a quarter here, or whatever cent piece you guys would have. And so it would be limited to about the 1700 microns that I mentioned, or 1700 nanometers, I should say 1.7 micron there. So that one's limited in terms of how far, but it can still see that 1450 water peak, which is convenient there. But the other thing is the sensitivity. So you're not getting as much of the pixel resolution or the sensitivity with the lower cost, limited, smaller form factor, but you get more of that sensitivity because then you can start, we have something called high gain mode, and then you can really crank up the signal on that bigger unit for the tower. And the other cool thing about the tower is that it has the, like I said, the multi-directional. So you can kind of get more snapshots at once over an area, but you also are limited to just that area that it's looking at, as opposed to the drone where you have more range and liberty to go around.
Thank you, Henrik, for a question. And yeah, if we don't have any more questions, thank you again, Derek.
Oh, sure thing. Thanks so much for having me.
Thank you. So now let's move on to our next speaker. Welcome, Therese Kuster. Therese, you are a senior scientist data capture and automation at KWS Group. and we'll talk about digital phenotyping in plant breeding. So please, Therese, the floor is yours.
Okay, I will share. Okay. Yeah, thank you, Jeremy, for the introduction. First, I will shortly introduce KWS because probably not everyone has heard from KWS, even though everyone regularly consumes products made from our plants. So KWS is a plant breeding company with a long tradition of about 170 years. We started with sugar beets in 1856, and today we have breeding programs for 23 different crops, and we work in more than 70 countries. For sugar beet seeds, we are the world market leader. Breeding is a long process. The development of a new crop variety takes on average about 10 years. So for the selection process, we need phenotyping to be able to reject several varieties after each test and to have at the end the best of all tested varieties. And with digital phenotyping, we do objective and non-destructive measurements, and we can acquire data more efficient. And so we have a high throughput. And all this enables a sharper selection than with conventionally phenotyping as possible. And yeah, with the digital phenotyping, we reduce the time needed for the breeding process. That's the reason why we do this here at KWS. Yeah, at KWS, we have several measurement systems on different scales because of many different traits the breeders are interested in. So today I will show you a selection of them. One important data source is the acquisition with drones in the field. Therefore, we have GNSS-based seedings in the field. And with the exact geo-registration of the image, we can derive the breeding relevant features for each single breeding plot. Here on the images, you can see as example, a part of a field with the breeding plots and some different data source for RGB, HSI, hyperspectral data, and a digital surface model and multispectral data. And I have overlaid also in red the polygons of the breeding plots. And yeah, here you can also see that we here need a high spatial resolution so that we see the single plants, which is necessary for our breeding task. For drones, we have some general challenges for our daily business. Weather and sun positions are a big challenge because we need regularly comparable data. And sometimes there are clouds or haze, or then we cannot fly with hyperspectral data, or there is a strong wind, then we can't fly anything because the drone will get stability problems. Yeah, and then we also have the issue with large data sets. They are really challenging. Yeah, on one hand is the processing time, and on the other hand is the handling and the storage of these large data, because sometimes in the season, the breeders need the data very soon after the data take for their decisions. Additionally, we have also need of high data throughput because the breeders have their tests every season on many different stations in different countries, and they have also want temporary resolutions. So we have really a big amount of data we have to handle. Here you can see an example feature for plant count. We measure it with RGB in the beginning of the season when the plants are small. And you see we have here really high spatial resolution. And our pilots are very skilled and trained to be able to fly at such low altitudes. With RGB, we can also create a digital surface model. And we need RGB for object detection and to train deep learning models like here for plant count. This is an example of hyperspectral data or feature we derive for biotic or an abiotic stress test. We need to know which breeding plot has more or less healthy plants. Therefore, we use the classification of hyperspectral data to distinguish between healthy plant pixels and damaged plant pixels. And we have also to exclude the soil pixels. The hyperspectral data have the big advantage that we can measure with a high spectral resolution, and so we can detect the vitality changes of the plants. But for high quality hyperspectral data, we need sunny weather, and yeah, in Europe, during summer we often have clouds, which is not so nice for hyperspectral measuring. This is an example for a feature measured with multispectral data. This vegetation coverage, yeah, this is really easy. We calculate a vegetation mask with a vegetation index, and then we count the pixels. Yeah, the big advantage of this data source is that we can also fly during stable, I would say stable cloud conditions because of an additional irradiance sensor on the drone. Yeah. Yeah. Recently, there are also limits for us in the use of drone data, especially for biotic stresses. With hyperspectral, we are able to detect vitality changes on plant level, but for early detection of diseases or also for the discrimination of the disease, we would need very high spatial resolution of hyperspectral data to be able to measure on leaf level, like here on the images. You can see different diseases on the leaves. But if we would do this, we will have trouble with the data amount and also with the flight plans because of the small swath width of our hyperspectral sensor. Yeah, we cannot manage this in one flight with the drone. So another limit is the spatial resolution of RGB sensors to count ears. If you fly so low that you can see the ears with the horns, like here on the left image, then the ears and the tillers will moving because of the wind made by the drone, and then the image is blurred. So then, we have also experiments in the greenhouse. Here you can see our Pheno factory in the greenhouse. Therefore, we have the plants in standardized pots. You can see here, yeah? And we can move these standardized pots with some autonomous robots. You can see here these flat objects, and they bring the plants here inside this box. And in this box, we measure the plants. And the whole measurement is fully automated, and the data are recorded regularly. We measure RGB and hyperspectral data in the visible and near range, and also here indoor in the shortwave infrared. And yeah, we measure recently twice a day. So the sensors are really busy. And one big challenge here is the light condition versus the signal to noise ratio and the demand of high data throughput. Often we don't have the time for long exposure times, and unfortunately the light is not powerful enough for high signal to noise ratio with low exposure times. So we often need to balance between quality and high throughput. And here on the image, you can see the noise here in the visible and also in the near range. And on the right side, you can see in the visible, it's okay, it's acceptable. And the right spectrum, I would accept for our analyzers, but the left spectrum, yeah, is not useful for us. Another challenge is the reliability of the sensor, because in the Pheno factory, the sensor is measuring for several weeks, many hours each day. So he's really hardworking. And here on these images, you see several measurements during a day and how the sensor is then stressed sometimes. So then we got this overexposure, which is due to sensitivity loss. Now I like to present something a bit different use case of digital phenotyping. This is the mini rhizodrone monitoring in the soil. So we do digital phenotyping also in the soil. You can see here these pipes or tubes. These are transparent. No, here, you can see it here. These are transparent pipes and tubes. And we install these transparent pipes under our breeding fields with the help of specially made machines. And during the season, a camera is guided here through these pipes and to image the roots from the plants. Here on the upper left, you can see we have many tubes inside. And it needs some time to put the camera, which is here on the right image, here inside, and then to measure all the roots. We work here with RGB, but it was really challenging to find first the right materials for the pipes, and also to find the right flashlight to get good images and to avoid specular reflections. Here you can see an image of such roots. But our colleague is really satisfied with the results, and he got nice results for drought and irrigated roots. So yeah, now I'm on the end of my presentation, and yeah, I thank you for the attention, and I hope it was interesting for you.
Thank you, Therese. Yes, it was. So any question for Therese, please raise your hand. Yes, Gaetano, please.
Yes, so thank you so much for the presentation. It was very interesting. You showed several cases in which you used hyperspectral imaging or multispectral imaging, so you always needed an image. Are there cases when point measurement for spectral measurement would be enough for your applications?
In some cases, for some traits, we also measure point measurements, but most we have images, and then our task is to reduce all this amount of data and to retrieve good information with which the breeders can work.
I see. Thank you so much.
Thank you, Gaetano. Yes, a question from Tobias, Ipsen Photonics.
Sorry, I don't understand.
Yeah, we can't hear you, Tobias. Don't know why. What's happened? You can write. Yeah.
Maybe it helps if you put the microphone in front of my mouth.
Yes.
Yeah, not
Yeah?
so good. Yeah, it's better.
Okay. Sorry for that. Nice talk. I was just wondering, you mentioned you had limited integration times on with the AMR, for example. What time frame are you talking about?
The exact number I don't know, but it is low. The problem is we have a 3 meter between the center and the plants, and yeah, there is no light which can light up the plant and the room so much that our SNR is good enough so that we are satisfied. So we are trying something else with different distances, like with 1.5 meter, and to high up the quality of our spectra. But the problem is we have many plants, and all these plants must be measured twice a day. So the robots go move, and the plants in the greenhouse and back to the measure to the sensors. And this needs a lot of time if you will measure all the plants. And we have many robots, so they are like in a long waiting line, and we cannot wait so long for a measurement for one image. And we measure not only hyperspectral, we measure also RGB, and I think it's not possible to measure it at the same time. We can measure it only afterwards.
Okay, thank you.
Thank you, Tobias. You mentioned, Therese, that you would need, a better resolution. But on the other side, you would have more data to
yeah, that's the...
So what is, how do you approach this challenge, and what would you need, today to overcome this?
Would I, for example, for this ear measurement, I think it would be nice to have a wider swath width, to have a wide open angle optics that we can fly higher, and then I think it would be helpful. We have a camera, I think, with a fixed optics, so if it's possible to change the optic, or I noticed from other manufacturers that we can change the optics. Yeah, this would help. And for data throughput, yeah, we are working on this, and the computers become better, and also the storage becomes better. And yeah, we are working on this, but it needs some time. It's developing. It's a process.
Okay.
And for the Factory, I think it was really cool if there will be good lights. And also the problem is not for the visible, the problem is for the shortwave infrared region. And I talked to other suppliers. They told us that there are no any lights on the market now because halogen is not so suitable any longer. I don't know how. It was what we got. And LED is not possible in the shortwave infrared. I don't know if you can help us. We are interested in.
Okay, good to hear. I think that we should plan a meeting together afterward, but I'm pretty sure that some people will be interested to work with you. So thank you, Therese. Thank you very much for your nice presentation. So now we can move on with our next speaker. Welcome Gaetano Panagia, Technical Marketing Engineer at Hamamatsu. And Gaetano, you will talk about spectroscopy in precision agriculture and food sorting. So please, Gaetano, you can start.
Yes, thank you so much for the introduction. So yes, I'm Gaetano Panagia. I'm a technical marketing engineer with Hamamatsu Photonics Europe. And today I want to show you a few techniques that are applied, spectroscopical techniques that are applied to precision agriculture and food analysis. Just a few words about Hamamatsu Photonics. For those of you who are not familiar with the company, we are a Japanese company, and we produce optoelectronic components. So we produce light sources and semiconductor detectors, but also complete systems. What I would like you to focus on this slide is that we have more than 15,000 products in the market, and most importantly, that 2/3 of these products are custom specific. So we always welcome customization requests from our customers. But diving in the topic of today, I've identified a few challenges that may affect this market. One of these in farming, for example, is the optimization of production yield due to a growing population. Of course, we need to adapt to climate change with more and more harsh events and difficult climates to grow our food into. And then, of course, we have the final goal of minimizing pollution with any activity that we start. And I think that spectrometers can help definitely to tackle all these challenges. We've already described a little bit how diffractive spectrometers work. So basically, the light reflected from a sample is split, is dispersed into its wavelength components, and then each component is focused on a specific pixel of a linear image sensor. So that's how we get the information about all colors, all wavelengths of a sample. And this wavelength contain very interesting information, specifically when we analyze a crop, as we have seen with the previous speakers, there is parameters like the green chlorophyll index or the red chlorophyll index, which are measured at 530 and 730 nanometers, that can be used to assess and map crop health. And this can be done using UAVs, so using drones, as we saw. Can also be done using tractors that can use the information to optimize fertilization, for example. And this can happen even more easily if the device that measures these wavelengths is as small as your fingertip, like the one that you're seeing in this slide. But this is not the only application that these small spectrometers can have in agriculture. In fact, another possibility of use of this is in water quality analysis. Of course, we use extensively water to irrigate our crops, and also we need to collect water back and analyze it if we applied, for example, chemicals in the field and we want to check for water quality after the farm. And this can be done again with these extremely small devices, pairing them up with xenon flash lamps, for example, in this lab setup that we have developed, in which you can see this is fiber coupled, and you have several vials with different chemicals. Specifically, we have nitrite, and BOD. And this is measured using the light coming from a xenon flash lamp, which bounces back at the end of this holder. It crosses all the samples and it's able to measure the concentration of each of them. This is a practice that would be done normally in a lab, so it will require some time to get the results. But with such a small device, these results can be obtained instantly. Other challenges in the food processing industry may be to establish nutritional values of our food, to detect possible adulteration. So, for example, if we have high-value goods like olive oil or wine, and this can be tampered with lower quality chemicals in it. Or we need more and more today to track the origin of food. So we need kind of a fingerprint that tells us what's in any kind of substance that then is used in the food transformation chain. And for this, we also have a solution, and it's a spectroscopical solution again. It's not a diffractive-based spectrometer, but it's a Fourier transform near-infrared spectrometer. You can see in this little video that I have that we are measuring in real time, we're distinguishing in real time the composition of this powder, which can be sugar or can be aspartame. And this can be done at 175 frame per second, so it can be done in line, basically. So it's very useful to analyze the ingredients in food. The principle through which this works, we have, again, light which is reflected off a sample. This light gets into this little scheme here. We have a beam splitter, so the single beam coming from the sample is separated into different arms, so into different beams. One reflects off a fixed mirror, while the other one hits a movable mirror, which is our special MEMS technology. And when these two arms recombine, they create an interferogram, so this kind of figure. So signal intensity and relative mirror position, it's what you can see in this graph. When we run a fast Fourier transform over this interferogram, that's when we get the absorbance spectrum of the sample between 1,000 and 2,500 nanometers. So this is what you're seeing here to the right, the one that gives us the possibility to distinguish between sugar and natural sweetener, so aspartame. This device can be, this kind of technique can be used in other applications. For example, you can imagine if you are a dairy producer and you're getting milk from several farmers, so from several sources, you want to check each raw material for homogeneity, for example. So you want to check your raw material before you put it into your product, before it enters your production. Another case could be determine the price of animal feed, which is an important application because the price of animal feed is determined by its nutrients. So how much proteins, how much fat, how much moisture is in animal feed. So using such a device or using Fourier transform spectroscopy, we are able to establish how much of these components is in animal feed, and then we can determine the price for it. The last challenge that we see in this market is bridging the gap between the end user, which has the knowledge about the application, and the technology providers, like we are, many in this room today. So at Hamamatsu, we think we can offer the bridging of this gap because we are producers of light emission components, we are producers of light detection components. We have the know-how to integrate this together into an optoelectronic module, and we can also make this module customized for the need of the application. So we have this new service that is called Pilot Line, in which we want to do exactly that. So combining our different components to make a prototype and make this prototype with a specific design intended for final mass production. So definitely what we want to do for you is to bridge the gap between your knowledge, your application knowledge, and our photonics know-how. Thank you so much.
Thank you, Gaetano. Thank you very much for your presentation. Any question for Gaetano, please? Regarding your last slide, about challenges in bridging end users and technology, it's something that we also see at EPIC, on this topic especially. And I wanted you maybe to elaborate a bit more on how you work with end users, because it's always difficult when they have to stop, for example, a process line to implement some specific solution. It's always a big deal for end users. So how do you work with this? Can you elaborate a bit more on your way or working?
Yes, of course. So obviously, we do have some technology, like I said, detectors and light emitters. We do not have all technologies available. For example, we are not expert in optical design. So what we want to do is, so what we're doing is getting the applications from the end users who, as you said, don't have the capability to establish a pilot line or anyway a production line for a module. And we have that possibility because we have been doing that for years. So what we want to do is just develop for them a customized module. And sometimes, as I said, we may not have all the expertise that is needed. In that case, we will partner up with people that will integrate our know-how to complete the module.
Okay. Yes, Enric from SPIO System, please.
Yeah, hello, Gaetano.
Hello, Andy.
Nice presentation. I just raised my hand because you said that you do not have all the expertise in-house. We might be able to offer you some know-how in small form factor of optical systems, passive optical systems, not active components, but let's say optical engines. We can do very small optical systems on wafer level. So maybe there might be a match in our cooperation with Hamamatsu in that respect.
Definitely, I thank you so much for bringing that up. Yeah, I think we should connect, and then maybe we can present each other's capabilities, so then we can collaborate in the future. Definitely.
Okay, thank you.
Yeah, perfect. Okay, thank you again, Gaetano, for your nice presentation. Thank you very much.
Thank you.
And now welcome Marc Larive from Exasense. You are Director of Business Development, and you will talk about Exasense advanced imaging benefits for agriculture and food industry. So Marc, please, the floor is yours.
Thank you. Hello, everybody. Can hear me?
Yes.
Good. You see my screen?
Yes, not in presentation mode yet.
And now? No.
Yeah, perfect.
Good. Okay, thank you very much, Jeremy. Hello, everybody. So my name is Marc Larive, and I'm Business Development Director for the Exasense Advanced Imaging company. So it's probably a new name for some of you. Just to let's connect the dots. Exasense is the group name of what now Xenix is part of. So you probably more know the Xenix name, which is a company involved in shortwave and longwave cameras and sensors, with long history in food and agriculture and technology. As previous people said, typically we are a technology supplier. So just to help you understanding who we are, so Exasense, we are an innovative company, and we are dedicated to amplification, detection, imaging technology components, for safer word. So we are, let's say, big medium company, around 2,000 employees all over the world, with just a bit less than 400 million euro. And yes, we are really around the world with more than 70 countries, very technological oriented. And we have 4 main segments: life science, industrial control, nuclear sensor for nuclear plant, and an activity in defense. The group itself is 85 years old. So let's focus a bit more. Today, the purpose and the activity is typically in between life science, environment, and industrial control, because it's a control application in environment and life science. So it fits exactly in our segment of application. So for the business unit advanced imaging, we do cameras and sensors with, at the end, digital information. So we are located all over the world, but the main part is in Europe, with the headquarters of the business unit in Leuven, in Belgium. And what we do is sensors and cameras from the UV, including lower than 200 nanometers, up to long wave. So we really provide the technology. The use of it is for plenty of application and semiconductors, but also a lot in food and agriculture industry. Again, we make the sensors and the camera. Typically, our policy is not to compete to our customers, so we stop at the sensors and the camera, but we provide technology for hyperspectral imaging, spectroscopy, and so on. But our contribution there is just a sensor. The spectrometer, such as people of Ocean Optics, is one step ahead. It's not us, but our skill is really the sensor and camera. So where are we and where could we be in agriculture and food industry? So let's say three main kind of application. All what is global vision, aerial vision, or it could be on mast also. But for us, it's typically global vision. And here, we focus on system on cameras that are compatible with a small payload. So typically it can be integrated in drone. So here we have some shortwave product and some long wave product, depending on what you want to see. Then we have also an offer dedicated for quality monitoring. So here again, mainly in shortwave, but for here we are more in machine vision and control industry, with shortwave spectroscopy and shortwave hyperspectral. And we see that hyperspectral is more and more the trend, and several people before me already talk a lot about that. And then also for the food sorting and grading, so it's after. Here we provide system for sensor for SWIR imagery and SWIR spectroscopy and hyperspectral. So first of all, global aerial vision. So what is the benefit with a shortwave? So it's typically the monitoring and of the health of the plant and what you want to grow, and detection of disease. So here again, our goal is to provide cameras that are compatible with drones, so that you can fly over your field and make the detection. We do that in shortwave, also in long wave, because long wave is used for typically water stress measurement. And again, it's even more compact in shortwave, so in long wave, excuse me. So compatible with smaller and smaller drone. If you remember, years ago, everything was done by planes or helicopter. Now, thanks to the evolution of technology, it's compatible with small drones. And to be compatible with small drones, the main requirement is to have something small, a camera which is small, which is light, which is not very power demanding. So what we call SWAPs, size, weight, and power optimized. So here we have different kind of camera. In shortwave, we have VGA camera, high speed camera up to 300 Hertz, the full VGA frame. So The resolution gives you an accurate registration, so it increases the precision of your measurement and thus the treatment you will apply. So at the end, you will reduce the chemical quantities and you optimize your cost. Because it's very sensitive, because we choose the kind of big pixel, 20 micron pitch, so you get a lot of light on each pixel. So you increase sensitivity, and because you increase sensitivity, you increase the performance of the detection and the yield. And because it's compact, you can integrate it on a drone. So it's really drone compatible. We also have a smaller, an even smaller camera here, which is ultra swap, so you can put it on an even lighter drone. Okay, because it's smaller, it's because the pitch is smaller, so it's a bit less sensitive, but it's still very highly sensitive. So you can again have a very, let's say, accurate trace detection. So that's for the shortwave cameras. Then we have the long wave cameras. And here, definitely, we are speaking about ultra swap. So VGA to SXGA, so that means from the TV format to the megapixel resolution. So you can get very high resolution with this. Easy to integrate, shutterless. It's at the end, it's compatible with different kind of environment. It's very swap. When I say swap, just to give you an order of magnitude, we are speaking about some grams, some milliwatts. I think it's 700 milliwatts, 10 grams or something like that, with a size of 20 by 20 millimeter by less than 10 millimeters. So it's really teeny. So you can integrate it even in a small game drone, let's say. And it's very easy to integrate because it has been designed for that and it's compatible with the machine vision interface and with a standard interface. And then we have the microcube, which is even smaller than that. Then for the application of quality monitoring, here the goal is more to make spectroscopy or hyperspectral imaging to really measure the chemical content. It's not just imagery, it's much more than that. And we have to design, and we design some specific, again, technology, sensors and camera for that. Very sensitive, very small, so that you can even operate it on the field in a portable environment. So again, the side of the environment is our customer decision. We provide the technology which enable a very small system. And for SWIR hyperspectral, here it's the best of both. You have both the imagery and the spectroscopy. So you can measure the chemical content at each location. So let's say the first one is more a point measurement that you have to scan. The second is really an imagery. So here we develop some line scan, very small system for spectroscopy. So really dedicated for spectroscopy, rectangular, small, compatible with micro spectrometer, really portable equipment with specific features that are relevant for spectroscopy, so that typically you can adapt your dynamic depending on the level of your signal in real time, for sure. You have an additional feature to even increase your signal to noise ratio to get a better detection and to really be able to say whether, yeah, this is a good product, this is a bad product. So you can, in real time, on the harvest, or even during the harvest, say, yes, this is good, this is bad. Okay, plus some additional features which are interesting if you put in front of the remark from Therese. If I remember, she said we we have to handle with too much data in the future. That's a limitation. One of the feature is to be able to select just the part of the data that you want. So don't register a full spectrum if at the end you only need 3 or 4 wavelengths or channel. Yeah, just register this one and focus on this one. So we provide solution for that. And then for the hyperspectral, here we are more speaking on 2D sensors and camera. And again, here what you need is precision, precision on the width to cover the wider size, and also precision on the channel, on the number of channels. So with a VGA, you have plenty of channel up to 512. So it's usually more than enough. And here it gives you, again, increase in precision, and at the end of the year, you will obtain. Very sensitive, because in hyperspectral, as it has been mentioned, you don't have a lot of light. So you are starving from light, and you cannot always put a big lamp, and especially, as you said, halogen lamp, it's more and more difficult, so you have to select it. So the light budget becomes an issue. So now we have solution very sensitive, even when you have few lights. And again, it's small so that you can integrate in a compact system. And then the final step, which is when the food is almost ready, here you need to sort it to say, okay, this is good, this is bad. So that's the first level of sorting. That's what I call imagery technology, where you sort the foreign object or the bad object from the real food you are looking at, typically gravel from grains. So that's a well-known technology, and here we have solution to make the imagery, and because of the contrast between the good and the bad, you can sort. And the next level, which is more and more important now, is to be able to grade. Somebody before my presentation mentioned that could be because of the price of the good that you have at the end, but it could also be because of the use. So depending, for example, on the meat, you can grade the meat, be able to say, okay, there is this percentage of protein, this percentage of bones, this percentage of fat, and based on that, you can say, okay, it will be at that price, but also it could be at that for that purpose. You can put it for pets food, or you can put it for human food. So typically that's one of the applications. And here you can do that thanks to hyperspectral technology. And again, here we have technology, we have sensors and camera that helps this sorting and this grading. So here it's for imagery, but usually you do that on a moving system. So either free fall, either on a belt. So just a line, a very fast line camera is enough. Square pixel here. But again, you need high sensitivity because you cannot integrate long time. You have to be on real time, so it has to be sensitive. Depending on the resolution and the width you want to measure, we have small line 512 pixel up to 2048 pixel for very high resolution or very large belts. And we have, as I said, very fast system running up to 256 kilohertz to full line. So here you can increase the throughput. You can also imaging multispectral if you don't want to do real hyperspectral, but with multiplexing different LEDs. And for sure, we can adapt the gain, the sensitivity, signal to noise to the signal you are looking at. And for hyperspectral, Here we usually provide 2D array cameras, so classical camera, VGA format. And here again, sensitivity is key. The format 640, 512 to get enough width and enough channel, and the speed. The speed here is key because you are looking at a push broom, usually, and or let's say whatever the technology you use. You need to run at very fast and very high speed to get at the end a real-time measurement. And the faster you can get, the better throughput you can get. So again, that's what we can offer, and that's the advantage you will get at the end on the agriculture and food industry. And that's all for me. If you have any question, I will be very happy to answer.
Yes, thank you, Mark. Yeah, we have one question, and we'll take one question because we have a lot of. Okay, we'll take two. Okay, let's start with data optical. Okay, Oliver.
I speak too much. I'm sorry for that.
Come forward.
I know.
Oliver, please.
Sorry, was me first?
Yeah.
No, yeah. Yeah, thanks, Mark, for the presentation. I wonder if you also supply the optical filters necessary for the spectral imaging, or if that is done by your customers or system integrators.
So usually it's done by our customers / system integrators. But if it's a filter that we can integrate directly in the camera, typically, yeah, we can provide it.
Yeah. Okay. So let's maybe talk afterwards.
Yeah.
Thank you.
Pleasure.
Thank you, Oliver, for a question. We had a question from Christine. Christine, if you want to ask your question, we can take time.
Okay, maybe it was part of your answer to the first question, because I would have been interested in your customers, specifically for aerial vision and quality monitoring. And I've learned that, of course, it's a system integrator. But maybe I ask the question, who is then the end customer? Is it an individual farmer? Can they afford the system, or is it a service company or drone operator? Would you like to comment on that?
Let's say, as we are selling to system integrator, it's a bit difficult for me to answer that. I suppose it's both, in fact, depending on the size of the farms or industrial farms, let's say, or on service provider. And on the food, it also will be both, as far as I know.
Okay, thank you.
Thank you, Christine. And thank you again, Mark, for your presentation. Thank you very much.
Thank you.
Now welcome Ariane Tib, Scientific Director at IMEC. Ariane, you will talk about laser speckle for non-invasive sap flow monitoring in plants. So please, Ariane, the floor is yours. You can start.
Yes. Oh, sorry.
Wrong screen.
Right, huh?
Yeah, presentation
okay.
One. Right.
Okay, yes, so thank you for joining. So yes, Scientific Director of One Planet. So One Planet is the collaboration between IMEC and the Belgium Research Institute on Silicon Integrated Photonics, Wageningen Agritech University, and the Medical University of the Radboud University in Nijmegen. And within One Planet, we focus actually on 4 different themes, which is agritech, environment, health, and food. And we have many optical sensing, many other sensing technologies. But a lot of data is required, a lot of sensing is required. But here within this talk, I want to focus on sap flow in plants. And if you look at plants. So very schematic images they are presented on the left. So the two primary vascular tissues in plants consist of the xylem and the phloem. The xylem in blue, and the xylem transports water actually from the roots to the leaves, and the phloem transports sugars, for example, produced in the leaves back to the roots. So the xylem is more or less the dead tissue, is the woody tissue, whereas the phloem is the live tissue. And if you look at the cross section, and in the center image is a cross section of a tomato stem, where you see these vascular structures nicely aligned together, where the xylem is on the inner side of the stem and the phloem is on the outside of the stem. So why do we want to do that? So, well, step flow is incorporated in plant models, and these plant models are used to characterize plants and to understand plants. But the step flow itself is not measured, and it's extracted from climate parameters of the greenhouse, for instance, humidity, light, soil, substrate, water availability, etc. But there's actually there's a need to implement or to include step flows into the mechanistic model of a plant. But step flows are really complex, so nobody really understands how the flows in plants actually are going. So we think that we can do something with it using our optical technology, and then especially using laser speckle. And here in this image, it shows a very schematic representation of laser speckle, where you use a coherent light source to illuminate the plant, and the light is reflected back, and it interferes, and it creates this speckle image consisting of bright dots and by constructive interference, and black parts of destructive interference. And this is what we're trying to use. And on the left, actually, you see, and I don't know if you can see the moving image, but it is a moving image where we use an imaging, laser speckle imaging, where we image to create an actually image of the leaf, but look at the speckle, and you see some of the speckles they move a little bit, or they flicker, go from black to white, and so that gives an idea on or is a measurement of the step flow actually in the leaf. But you can use mathematics, and then you can extract the image on the right, which actually is a representation of the flow speed in particular parts of the leaf, where you have high activity and low activity. But this is quite complex, and we want to simplify it, of course. But first, let's see at the data analytics, so how it works. So what you do is actually you record a sequence, just a video of laser speckle images, and you look at the variation of intensity pixel by pixel over time, and then you use. For example, we use LASCA, which is laser speckle contrast analysis, pixel by pixel over time. So you get a whole nice line of intensities varying over time. And you can do the contrast, the temporal LASCA, which is looking at the contrast over the average intensity over time. And the other technology we use mostly is the G2 or the DT or the D2 functions, which actually extract the time correlation constant from the speckle data. So how constant actually is the speckle data over time? So if the speckles, or if the intensity in a single pixel doesn't change over time, then basically there is no flow. If the speckle intensity changes over time, there is flow, and the more it changes over time, or the faster it changes over time, the more flow there is. So that's the basic idea behind this. So where we are today, so this is our prototype that we have several of these prototypes that we are evaluating at this time. It consists of a laser, of a camera. The laser is directed towards the stem, and we look with the camera at the speckle, and then we analyze the changes in intensity pixel by pixel, and then extract from that the SEP flow. And in the graph over here on the right, you see the day and night rhythm. So basically, the SEP flow in the xylem, it works by evaporation. So there should be light, otherwise there will be no evaporation at the leaves, and there will be no flow. So that's why you see these big differences between day and night. Where the blue is actually a standard sensor, which is called a heat balance SEP flow, which is our reference, and the red one is our laser speckle data, where we see in general you see much more, where you pick up much more variations in the speckle data compared to the heat balance measurements. But in the end, we want to make it smaller and smaller, and we want to move towards a laser speckle sensor that has a clip-based format, where we don't use an image but just measure the speckle intensity, well, just on an average image actually, where we can measure the SEP flows in the stem towards the leaf, towards the fruits, to characterize the plants, which is interesting for breeders. Yeah? So because you want to have the most of the flow going to the fruits, so they develop the best, and the high, to have the highest yields, and we want to have this spec or this clip run on a wireless battery operated, and it should be small, and it should the battery should at least last the full production cycle, in this case of a tomato plant, which is, well, I said 3 to 6 months. That would be very ideal to do. So that is what we are working on. So today we have one laser. We want to move to 2 lasers, or maybe even 3 or 4 lasers, looking at different depths to get a better idea. We don't know what data that will actually give us. We will find out how it works and what will it tell us about the health status of the plant. And in the end, you want to implement or integrate this SEP flow measurement into the climate control system, whereas currently the plant status is now determined by the grower by simply looking at the plant and say, well, I need a little bit more humidity, higher temperature, etc., more light. But the plant status itself is not part of the greenhouse climate system. So by having these SEP flow sensors, hopefully the plant status can be included into the control loop for the greenhouse climate. And well, you see this already happening. It's with greenhouse systems becoming more and more autonomous. So it's really needed to have these sensors, and we believe that SEP flow can be a very nice sensor to add to this control loop. Well, with our technology, with our in-house technology on integrated photonics and low power and wireless communication, we think we are able to create this very nice laser speckle sensor. And with that, thank you for your attention. And so if you're interested in working together with us on further developing this clip size-based laser speckle, joint applications or other opportunities, well, feel free to contact me. Thanks again.
Thank you very much. Very interesting project. I didn't know about this kind of application of laser speckle. Any question for Ian? So what is the TRL of your product, of your technology?
Well, you saw the prototype sensor that we have today, right? So that is on the TRL level 5, 6, somewhere in that order. So it's being tested now at tomato plants, and on the same time on the laser speckle clip. It's not there yet, so the idea is to go from the prototype, which is already quite small, to establish the parameters that we need, and then to move on to the smaller version of it. So I would say TRL 5, 6. Okay, and do you need any support in the product development, making it more compact, more light, more optimized for that application? Yeah, well, as you know, so we have a lot of technologies already in house, of course.
Yeah.
On the product design, yes, we can use help there. I think the same as on the application side. For instance, a KWS can be a nice application. How to say it? Company that may use our technology, and well, so that's
Yeah.
what we're looking for.
Also in a vertical farming industry, it could be
No,
quite.
yes, on a vertical farming industry, yes.
Yeah.
Tomato. So inside, outside is all fine. Yes.
Yeah, very interesting. Yes, Enric, please.
Yeah. Hello, Adrian.
Yes,
Thank you for the talk. You reach out to other partners in your development work. What competence do you need in your roadmap?
Yeah. So as mentioned there, so on competences, so we're very well. I think we have most of the competences. But it's more on the competences that we miss is know-how on the plants. So we get very nice laser speckle data out of it, but how to translate it back to plant status, to plant health. That is the know-how we don't have, and that's why we also work together. That's why it's also developed within One Planet. So One Planet, so we make use of the collaboration between Wageningen Agriculture University and IMEC as the photonics provider.
Okay, so it's not some kind of an hardware platform to be able to produce it more on the technology. How it's
Yeah, well,
characterized.
so on product development itself, so bringing the product from the TRL, now it's at 5.6, we will bring it to TRL 7, 8, maybe, that's it. And then somebody else has to put it to the market. So we don't bring these products to the market ourselves. We design it, we build it, we test it, etc. And then we move it to the companies that are interested to bring it to the market.
Okay.
So the plan is to send to sell licenses, right?
Yes, to sell licenses as well. You know, there are many different constructions on that. But that is something that business development is doing, not me.
Yeah. Okay, very interesting.
Yeah.
Yes, Alex from KWS. Alex, you are, yeah.
Quick question. As far as understood, there is no way to infer the real actual flow speed from the patterns that you actually capture, right? Or there are some approaches that could eventually end up measuring the actual flow speed.
Yes, it's possible, but it's not easy. So our first aim is to say, okay, given the laser speckled data that we have, we say, okay, the value, the optimized value should be around 7, 8. Let's say that if you say, okay, we have a value between 0 and 10, we want to optimize it at 8. Okay, then but it's not an actual flow speed. You can do that, and it is being done in health applications where they transform the laser speckled data back to actually blood flow measurements, or actually velocities. That requires really modeling the plant tissue. Yeah, but you can do that, but it requires more work. It's not our aim, at least. But maybe if it's needed in the end, then okay. Yes.
Yeah, thanks.
Okay, so thank you, Ryan, for the nice presentation of this technology. Thank you very much.
Thank you.
And thank you all for your question. Now we move with our next speaker, Rennie Hein. You are CEO at Qbert Hyperspectral, and you will talk about spectral snapshot imaging solutions. So please, Rennie, welcome, and the floor is yours.
Yes, hello. Thank you very much for the introduction. Just a question. Can you see my screen?
Yeah, yeah, perfectly.
Okay, great. Yeah, my name is René Heine. I'm founder and CEO of Qbert. We founded this company in 2012. And at that time, we were one of the only sources of snapshot hyperspectral imaging beside of IMEC, which came, in my opinion, 1 or 2 months later. I don't know. Who knows? So we do spectral imaging since then, and a lot of our customers use our devices specifically for agriculture research and agriculture developments. So the question is, why is hyperspectral imaging important for agriculture research? There are multiple reasons we see which get more important over time. So due to climate change, we see a lot of people's interest in changes of biological systems. So real-time data and easy accessible data is of high importance right now. We also try to bridge a gap between satellite data and ground truth data with a UAV mounted hyperspectral camera. And we see that there's a constant need of real-time data. Example given with KWS, we also had a short study in 2014 with your colleague. And unfortunately, at that time, our system was very limited in spectral resolution. So we only had 50 by 50 hyperspectral pixels, which was not enough at that time. Otherwise, we might have had a cooperation with KWS as well, which is a proto customer of ours. So what we do is full frame hyperspectral imaging. So we always look for solutions to get a complete spectral cube with one sensor readout. That is a bit different to the other gold standard of spectral imaging, which is push broom, which is also regularly flown by our colleagues from Headwall or similar. However, I would say it's much more complicated to make a spectral map out of single lines which they measure. What we usually measure is a complete image, and we measure multiple images and they create a map. So I think I was not sure if it was clear what hyperspectral imaging or spectroscopy in itself is and what the difference to multispectral is. I guess in the talks we had today, it was quite clear. So for us, the difference is usually twofold. The first difference is multispectral. It's usually you have single wavelengths and not a spectrum. Secondly, with hyperspectral, you sometimes have better classification results for chemical sensing. If you have just one issue or one topic you want to have your data for, then multispectral is totally fine. And we also sell multispectral cameras with customer-defined channels. Sorry for the sound. I hope the video is somehow transmitted. So we have a full integration of our solution in a DJI 300 drone, which is a very interesting platform for a turnkey-ready solution. The DJI system already brings us very far with a very good integration of a mapping solution, of the autopilot, of a triggering and generating of a map. So this system enables you with 1 or 2 days of training to make your own mapping. And the camera provides 350 to 1000 nanometer wavelength range and captures hundreds and thousands of images from the top. The flight. So this is the system. It's based on a DJI Skyport, where the camera is fully integrated. So the only thing you have to do is plug it in and install the current software of ours, and then generate your flight planning. This is how an image of our system looks like. We have a system which is twofold. We have a high resolution pan sensor, which gives you up to 1800 by 1800 pixels. This is used for stitching, and it's used for the high spatial resolution image or map you want to generate. Additionally, we have the hyperspectral snapshot camera, which has 400 by 400 pixels. Both are captured at the same time. And in the end, you can have a data product, which is 164 bands with 1800 by 1800 pixels. And this is just one image. So what we do when we fly is we capture one image a second or one or two images a second, and flying 10 minutes, and then you can imagine you have thousands of images with one map. The autopilot of the DJI flight system is programmed before the flight, where it should fly exactly, where it should capture the images. And after the flight, you will have, this is a very short map, by the way, you will have a multitude of images. Each of this rectangle represents one hyperspectral cube, and the direction of the UAV from which it was taken. And this is then fed into Argisoft Metashape, and a complete map, a complete hyperspectral map is generated. These data sets can be quite huge, so multiple gigabytes and such. The calculation of a data set like that can take a day. After the calculation, you have, in principle, a completely open data set which you can work with. It features a digital surface map, a 3D map of the surface evaluation, which already can give you some information, example, given the height of crops or biomass, applications I've seen people work on. But also you have multiple image formats and spectral calculations on the crops you are measuring. I have to admit that we are not the best experts in the applications itself, because what we concentrate on is have the easiest to work with flying hyperspectral mapper. And we have a big community of customers who are working in the agriculture field. So this is a survey we did a while ago, where we just went through the publications which were done with our systems. So we found 180 publications on a specific system. And we see that over 50% of our literature is in agriculture and food. This survey can be found on our website, by the way. So if you're interested in specific studies regarding applications in agriculture, that might be a good starting point to have a look. It's very extensive. But beside food and environment, we also have a lot of water spectroscopy, which tends to be similar because it's very often due to climate change. So we have a lot of customers interested in water quality, biodiversity, and the change of biodiversity during heating up times. But also if you are in forestry, which is very often CO2 related, so carbon, measuring the carbon footprint of forests is a big topic from our community right away. So overall, I just took, a very small chunk out of it. So you see, we see a lot of publications working on detection of plant health issues in multiple plants, in potatoes, in tea, in winter wheat, and so on and so on. So the amount of work which is put in by the community right now is tremendous, and we see still a rising amount of scientific research going on in this field. And we hope we can do our part to help our scientific community to be successful here. Yeah, it's quite some publications. So overall, I just wanted to use the chance here to say thank you to our customers, to be honest, because without them, we wouldn't be here. And we know that we can only do so much. And so I also want to say we are very happy about feedback. If there's any feedback here, we are super happy to know it. And how far our customers brought us is shown in this image, because I just pulled it up. This was the very first camera we ever produced. And this was for an agriculture application as well. So this is a gentleman from the Uni Hohenheim here in Germany, and they did mango analysis, mango health analysis. And this was in 2012, so nearly 13 years ago. And so the topic didn't change, just the technology changed a bit, and we try to keep up with the best technology we can provide. Yeah, thank you very much.
Thank you, René. Thank you very much for this nice overview. Any question for René? Okay, no question, no specific question. Maybe I can ask you, the big question. So what can you do is quite clear after your presentation. But what could they do for you? What would you need? Do you have any specific challenges that they could bring some solution?
I mean, from Epic?
Yeah, from the participant, from the ecosystem, Epic ecosystem.
That's a very good question. I'm very, very often in contact with Oliver regarding new filter technology. So I would say we are very well connected in your network. And I would say, or let's put it that way. Your network already pushed us to the limit. So the technology we have today, which is the slide feed hyperspectral imaging technology, was mainly due to the contact to your network.
Okay.
Regarding Oliver Poost, who is, how to say, or at least his company was a mental father of the tech. So yeah, we are very grateful to Epic as well.
Okay. Anyways, if you have any specific needs, feel free to contact us anyway, René. So thank you very much.
Thank you very much.
Thank you for a nice presentation. And now we will welcome Hugo Texera from the Retina project. Hugo, hello. And you will present the Retina project, and your presentation title is Vineyard Management through Photonics Innovation. So Hugo, welcome, and please, the floor is yours.
Oh, sorry. Good afternoon. I think you are seeing my presentation.
Yeah.
Okay, so my name is Hugo Teixeira. I'm a viticulture technician and a project officer in Collab Wines and Wines in Adviv. So we are an initiative that is dedicated to support the Portuguese wine sector through applied research and innovation. It was a title attributed to Adviv, that is an association of wine companies that was founded in Douro region. So in 2019, it was established this collaborative research. So these are our numbers. We are more than 200 associates and 70 partners. That includes wine companies, interface centers, and the institutions and tech suppliers. So in 2022, Adviv Collab Wines and Wines joined forces with 3 institutions in the center of Portugal, in the region of Dão, with the Dão Regional Wine Board, the Polytechnic Institute of Viseu, and the Regional Directorate of Agriculture and Fisheries of the center. And they create this hub to align the research of Collab Wines and Wine with agenda to another region. So they are the two of the major wine regions in Portugal. So regarding the Retina project, that we are a partner, and we are, I will make a brief presentation. So the Retina objective is develop advanced photonic integrated lidar and snapshot spectral images for scaling up multi-perception and precision applications. Developed, and there are two new technologies proposed. Novel data based on PHIX and quantum dots and optical microfilters for spectral imagers. So there are three sectors for validating our projects: healthcare, automotive, and agriculture. We are part of this use case, the precision viticulture. That we are 13 partners from seven different countries. The technologies involved are for two different platforms: ground-based platform, which includes short-range lidar, hyperspectral snapshot, and quantum dot spectral snapshot, and a drone-based platform, long-range lidar, hyperspectral snapshot, and a quantum dot spectral snapshot. So I will present more our use case is the precision critical. So we have three main goals: is the detection of grapevine trunk diseases, monitoring the water stress, and the harvesting the forecasts, yield estimation. So we have two validation platforms: the ground-based platform, a handheld prototype, and the drone-based one. So regarding the grapevine trunk diseases, are one of the major threats to viticulture because they hide damage that is only visible years later. So we need to identify these plants earlier to can stop the spread. So the type of diseases are through infected material introduced in the new vineyards from nurseries, and through pruning wounds that allow the complex of fungi to colonize the plant's vascular system. So there is no cure to this complex of diseases. So we need to not only an early detection and the removal rapidly the diseases plant. So Retina here addresses this challenge by combining LiDAR's structural measurements of the trunks and the canopies, and monitoring the whole plant, that trying to flag suspect vines through subtle signs that we cannot see in the field. Regarding the water stress, so the growers and us today rely on the per down lift water potential, but this type of measurements are very accurate, but it requires a lot of field work at night, and only provides point samples, which mean that large areas of the vineyard remain unmonitored. So we try to map through lidar and multispectral, hyperspectral imaging this water stress, allowing a better spatial distribution of water status of plants. And the third one is the yield estimation, harvesting forecast, that allow us to optimize our operations on the field and on the field, program or crop insurances, and a better management of the workforce. So regarding the harvesting forecast, the traditional yield estimates often rely on the counting flowers or berries or clusters by hand, so it's very labor intensive, destructive, and are prone to error. So the routine solution is to try a real-time estimation of harvest quantity with more accuracy. So in our use case, we have 2 experimental sites in 2 important regions, in Douro and Endão. So our monitoring schedules covers the key road stages. In this case, the pre-flowering for the yield and the grapevine trunk diseases. So from the bunch closer to very zone to harvest, we monitor the water stress management, the yields, and the grapevine trunk diseases. And at last, the harvest will monitor the water stress management, the yields, and the grapevine trunk diseases. So in the first phase of data collection began in 2024 season, included validating the experimental prototype, the handle health prototype, by measuring the leaf water potential, allowing work to begin on calculation of the correlations between the baseline water potential and the multispectral images obtained. So our colleagues later they treat the images, they uploaded to one of the partners' platform, the RAIA platform, for labeling and for construct our data set for our project. So thank you for your attention. So if you have any question regarding more the viticulture use case, be free.
Thank you, Hugo. Thank you very much for this presentation of the Retina project. I think that EPIC is a part of the project, not myself, but some of my colleagues are part, and we're in charge of the dissemination and communication, right? So it's a nice project, very nice project. So thank you very much, Hugo. So any question for Hugo to end this meeting? And if not, so thank you. We'd like to thank all of our speakers of the day. It was very, very interesting to hear about new kind of technologies. We talked a lot about hyperspectral imaging and drones as well. So everything was very, very interesting. We plan also maybe a technology meeting, physical technology meeting next year. So we'll see. We'll keep you informed, of course. And we'd like also to thank our sponsor of the day, PHIX, which sponsors this event. And so thank you for this. Thanks to all of you for your question. If you need to be introduced to one of the speakers today, feel free to contact us, and we'll be very pleased to put you in contact with them. And if you have any question, you can also contact us. So thank you very much to all of you, and see you next time. Thanks a lot.
Thank you.
Goodbye.